Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we're looking at our first section of 3.13, 3.13. This is going to be a video broken down into multiple sections. Today we are just looking at some basic trig identities as well as what's known as the Pythagorean identities. And we're going to be using those to rewrite different mathematical statements, seeing if we can simplify them to make them and reduce them into a simpler form. In order to do that, we need to remember a few things. We need to remember the different reciprocal identities. For example, we know sine of theta, or whatever the variable is. It doesn't have to be theta. It could be x, it could be y, it could be t. Whatever variable we have there, we know is the reciprocal for cosecant. We know cosine is the reciprocal for secant. We know that tangent is the reciprocal of cotangent. Remember, to find a reciprocal, you're flipping the fraction, but you could also just put 1 over that value. We know that cosecant is the reciprocal of 1 over sine, right? And we can just keep filling out this table super quickly. Again, reciprocal is just 1 over a value, but again, you can also just flip the fraction if it is already a fraction. So there we go. So, okay, that's some of the stuff we know. Some of the other stuff we know is the quotient identities. That means quotient, I think division. I know tangent and cotangent both have division in order to find their values. For example, I know tangent is the y over the x, but remember the y value is just the sine value. And the cosine value, the x value, there we go. We have a fraction, we have a quotient for tangent. Same thing with cotangent, but it's the reciprocal of it, meaning the x and y, or the sine and cosine, just flip in the fraction. The new identities we're looking at then are the Pythagorean identities. Well, if you think Pythagorean, you think Pythagorean theorem. That means you have some right triangle. We're used to A, B, and C, but we're looking at the unit circle, where the unit circle has a radius of 1. We're looking at the x value and the y value, but I know the y is sine and the x is cosine. So, okay, if I was looking at Pythagorean theorem, something like this, it would just be the same thing as x squared plus y squared, where our hypotenuse is 1 squared. So simplifying that a little bit, rewriting the different parts, I know x is really just cosine. I know y is really just sine. And now I have my first Pythagorean identity. Cosine squared theta plus sine squared theta. Realize the order of that doesn't matter. You might write the sine squared first and then the cosine squared. The order doesn't matter there. But okay, let's figure out how to find the other two identities. Let's figure out how to find the second one. In order to find the second identity, let's maybe say that we want to change it. And I'm going to change it by dividing. I'm going to divide this entire thing by cosine squared. Well, cosine over cosine there, those would cancel out, just giving us 1. Sine over cosine, I know, is tangent. Since they're both being squared, it's tangent squared. But the last part, I also have 1 over cosine. 1 over cosine is the same thing as secant. So now I've just made my second identity there. The third one can be found by doing that exact same process, but when you do the process, let's now divide by sine squared instead. The sines we know cancel. Cosine over sine is the same thing as cotangent. That's cotangent squared there. And 1 over sine we know is cosecant squared. Now we have our third identity. Cotangent squared plus 1 equals cosecant squared. So now what we're doing, now that we know what the Pythagorean identities are, we remember our quotient and our reciprocal identities, let's start to utilize that stuff and try and rewrite some of this. For example, if I want to try and rewrite sine squared theta, well, I know that sine squared theta occurs in this first Pythagorean identity. So maybe I just start by writing that identity down. Okay, but I want to rewrite it for sine. That means I want to get sine by itself. In other words, that means I need to subtract the cosine squared over to get sine by itself. Sine squared theta, if I rewrite it, it is equal to 1 minus cosine squared theta. Well, you can do that same idea for cosine squared. Instead, you could subtract the sine squared over to get cosine squared theta equals 1 minus sine squared theta. And you could do that for each of these. Well, tangent, if I want tangent by itself, that's 1 plus tangent squared equals secant squared. Get tangent by itself, so tan squared is equal to secant squared minus 1. Subtract the 1 over in this case. And you could just continue to use that process for the next two. If I got cotangent by itself, it would be equal to cosecant squared theta minus 1. If I got secant squared theta by itself, notice it's already by itself, so I already know that answer right away. And the last one, a value of 1. I know that value of 1 could have been found by cosine squared and sine squared. That value of 1 also occurs in each of these other formulas. Get the 1 part by itself, and you might have secant squared minus tangent squared. You might have cosecant squared minus cotangent squared. All we're doing is just manipulating these equations to get whatever part we need by itself. Sorry, that one is under the wrong one. I meant to put that under the 1. Okay, but all we're doing is manipulating equations. Well, let's continue to manipulate this stuff and start to break down a few more problems. For example, secant. It's not secant squared, so I cannot use the Pythagorean identities. But I know something else about secant. I know secant is 1 over cosine. Cotangent, I know cotangent is cosine over sine. Okay, well, guess what? Cosine over cosine cancels. This is just 1 over sine. But okay, I know something about 1 over sine. 1 over sine is the same thing as cosecant of x. So notice we're just taking equivalent steps, replacing things with what we know they are equal to. When two things are equal, they're the same. When two things are the same, you can replace them. You can interchange them. Let's look at another example, maybe D here. I see parts that are being squared. Cosecant squared, well, cosecant squared, you might try and find that given some of these different parts that would work. For example, if I go all the way back here, I know cosecant squared is this. Cotangent squared plus 1. So, okay, I could change this then to cotangent squared. We said it was cotangent squared plus 1. And then, okay, well, if I do that, notice I have cotangent and cotangent. Those are just being subtracted, so those are gone now, and we just get a value of 1. Right? That's one method to go through this. There's a variety of different ways. Another way you might do it, cosecant is sine squared. Cotangent is cosine over sine. These have common denominators, so I could combine them then. Okay, but 1 minus cosine squared, we knew what that was. 1 minus cosine squared is just sine. So now I've made this into sine squared x over sine squared x, and that also gives us 1, right? So there's a bunch of different strategies you can use. You just need to make sure you're replacing whatever part with an equivalent statement and using algebraically correct steps to try and simplify. And if you do that, you should get the correct answer. Let's look at E and G now. Some more examples of how this might work. Okay, well, 1 minus sine squared. Well, if I know cosine squared plus sine squared equals 1, then I know that 1 minus sine squared would just be cosine squared, right? I'm just manipulating that equation. So the top then could just be cosine squared theta over sine squared r. I guess these are r's and not thetas. Okay, well, that's cosine over sine. Cosine over sine, I know, is cotangent. They're both squared, so don't forget the squared. Okay, now I have this as a single trig function with no fractions. We're done. Okay, I look at G, and G might be a little bit more confusing because when I see these Pythagorean identities, I know the number 1 is in them, but I see this value of 3. I don't like 3. I don't like 3. It's not in any of those identities. Okay, well, let's get rid of the 3. Let's factor it out. It's been factored out. Well, notice the inside now has that value of 1. So, okay, maybe I look at this top equation again. Cosine squared theta plus sine squared theta equals 1. And again, we need to manipulate this. Or, better yet, I see cosine squared theta. Let's get that part by itself. Again, like we already did. So now this can become 1 minus sine squared x in this case, minus 1. Well, notice the 1's cancel. So all I'm left with is 3 times negative sine squared x, which is negative 3 sine squared x. There's a variety of ways to get these answers. You don't have to use the steps I am utilizing, but it is one way to get the answer. You may find other methods, other ways that work. Let's look at F. Notice no squareds. I cannot use Pythagorean identities. But I do know cosecant is that. I do know cotangent is that. I know that if I divide fractions, I can copy dot flip to change it to now that. Sine divided by sine is gone. This is 1 over cosine r. 1 over cosine r is the same thing as secant of r. And now I have another answer. This stuff I think is very fun to play around with. And if you try something and it doesn't work, try something else, right? There's a variety of ways to get there. If one of them doesn't work, try again. You just found a method that doesn't work. So now you know that you can use something else. I look at this next one. Again, we already found cosine squared plus sine squared is 1. So if I manipulate that and get the sine by itself, that's 1 minus cosine. So I know that the top then is really just sine squared x. The bottom, cosecant and cotangent, one of our formulas actually utilized both of those, and it was this. Well, maybe I need cosecant minus cotangent, so that would be 1 equals. Okay, well, now I can replace the bottom with just 1, and this is just sine squared x. And now we have another answer. I think this stuff is fun to play around with. I think it's interesting to see if you can come up and simplify these really crazy statements with something a lot simpler. Hopefully you guys agree. Hopefully we're seeing some patterns here, seeing how this idea works out. Thanks for watching. Come back next time for the other 3.13 videos.